All right, Bismillah ar-Rahman ar-Rahim. Today we're going to talk about a thermodynamic approach of an air source refrigeration system. My name is Nooraldeen, Hanie, Abdulaziz, Aldeeb, matric number 209586.
Assalamu alaikum. My name is Mubarak Awadh and my matric number is 209713.
Hello, assalamu alaikum. My name is Thoheer bin Nazif Emran. My matric number is 211633.
Assalamu alaikum. My name is Ibrahim alrubayan. My matric number is 213351.
The contents of the report for today, we have 7 parts, and we're going to be talking about them later in this slide. Next. All right, so for the first part, we have the literature review. We're going to talk about what a refrigeration system is and how the cycle works. But to begin with, the term refrigeration refers to the preservation and generation of a temperature lower than the temperature of the surroundings in a certain space or substance. This is made feasible by the absorption of heat at low temperatures and it's released at high temperature. The procedure is typically carried out by evaporating a liquid with a low saturation temperature at the evaporation pressure and returning the vapor to its original liquid condition for re-evaporation purposes. So as you guys can see in the cycles, the whole cycle consists of 4 operating steps. The refrigerant compression, condensation of vapor into liquid, liquid expansion, and in the end, the liquid refrigeration evaporation. So for the compression of the refrigerant, it's basically raising the temperature and the pressure of the refrigerant and receiving work for the compressor. For the condensation of the refrigerant, heat is going from the condenser to a high temperature reservoir, such as the environment or the atmosphere around the cold space. And for the number 3, which is the expansion of the expansion at the throttling or pressure valves, the refrigerant enters the valve at point 3 and expands and releases pressure with temperature drops continuously. Then it leaves at 4 as a liquid vapor mixture. And then at step number 4, which is the evaporation of the refrigerant here evaporates in the evaporator and it absorbs the latent heat of vaporization, where heat is being absorbed from the items or the refrigerated space and into the evaporator. Moving on. All right, so we're going to be explaining on the pressure enthalpy diagram. We have 2 ideal refrigeration cycles: the vapor compression, which is the pressure enthalpy, and the vapor absorption, which is the temperature entropy. All right, so for the vapor compression, it starts as a saturated steam, as you guys can see in the superheated vapor, where it is compressed, and then the entropy here is constant, and then the work occurs between 1 and 2 because the work goes into the compressor, as we said. As it leaves the compressor going into the cycle, it will be in an isentropic state from 2 to 3, where the QH is the heat released into the environment, or as we said, the atmosphere around the cold area. Number 3, it will go inside the heat exchanger, going back to the subcooled liquid, where the pressure is maintained, so the pressure is constant here, and it's located at the saturated liquid, so it's isobaric. Isobaric meaning that the pressure doesn't change. And number 4, getting into the throttling valve, where it is depressurized, hence it reduces the pressure from 3 to 4 while maintaining the same enthalpy because it's isenthalpic. All right, and in the end, the QL is just going out of the refrigerated space, but into the cycle. Moving on to the vapor absorption. All right, so the vapor absorption is a bit simpler. As you guys can see, it's the compression of vapor, the vapor superheat removed into the condenser and then converted to liquid in the condenser and then flashes to liquid. So just some quick notes on each part. Between 1 to 2, as we said, the pressure of the refrigerant increases. Then it is slightly cooled from the superheated to the saturated vapor, while it remains constant till 0.3. And for the pressure, it also remains constant while heat transfer occurs when heat is released from the condenser to the surrounding area. And the enthalpy and the entropy from 3 to 4, as you guys can see, remains constant here. So the temperature, yes, is reduced back to the temperature before compression, but the enthalpy and entropy remain constant. And last, the temperature then at 4 remains at a low constant with heat transferring from the refrigerated space to the evaporator. Thank you. And next.
So I'm going to talk about applications of air source refrigerator in different energy system. So the first one is electronic cooling application. Vapor compression may lift enormous heat loads and heat sink at temperatures below ambient. Cold blades can compensate for large case to junction temperature gradients in order to protect high power ingredient circuit from overheating and or decrease injection temperature to improve integrate circuit performance. Helicopter vapor cycle air conditioning system. Vapor cycle cooling technology is more widespread than most people realize. Once considered a luxury item, systems are now considered mission critical. There is a current legislative campaign to require air conditioners for helicopter emergency medical service (HEMS) operators. So I'm going to pass it to Mubarak.
Okay, so I'm going to talk about the methodology we used in our numerical model. So for the numerical model, the refrigerant used was the R134A, and the system parameters are mass flow rate and temperatures entering compressor, entering the condenser, entering the valve, and entering the evaporator, and the P1 and P2, which is the pressure before entering the compressor and the pressure leaving the compressor, and H1 through 4, which is the enthalpy before the compressor, enthalpy before the condenser, and the enthalpy before the valve, and finally the enthalpy before the evaporator. So all these systems that, the parameters that I just spoke about are used in our numerical model, and the parameters that we used in our theory are the ones on the right: the evaporation temperature, the condensation temperature, the mass flow rate, and using the R134A table, we can find the enthalpy values at stage 1, 2, 3, and 4, and also we can get the entropy values in all stages 1 through 4. So the unknowns that we had were the QL, the QH, the coefficient of performance, and the network N of the whole system. Okay, so moving on to the 4 steps of the ideal vapor compression cycle. So the first step is the compression of the refrigerant. The refrigerant goes into the compressor as saturated steam, and it leaves the compressor in an isentropic state. Or in other words, the process between 1 and 2 is an isentropic process. The entropy is maintained constant throughout, while the pressure and temperature both increase simultaneously. The work received by the compressor, work in or network N, which equals the product of the mass flow rate and the change in enthalpy or difference in enthalpy, where H2 is the enthalpy after leaving the compressor and H1 is the enthalpy before entering the compressor. So work in equals to mass flow rate multiplied by H2 minus H1. So the second stage, which is the condensation of the refrigerant. So when the refrigerant enters or reaches the condenser, the pressure is maintained, so constant. So P2 equals P3, and the temperature is decreased. The process between 2 and 3 on the pH diagram represents an isobarical process because of the constant pressure maintained throughout. The condenser heat capacity QH is released into the environment, where this process is equal to the product of the mass flow rate and the enthalpy difference, where H2 is the enthalpy before the refrigerant enters the condenser And H3 is the enthalpy of the refrigerant after it leaves the condenser. So Qn equals to mass flow rate multiplied by H2 minus H3. And third stage or step, which is the expansion and pressure release of the refrigerant. So at the valve or the expansion valve, where the refrigerant gets depressurized, the temperature and pressure both simultaneously decrease. The net work done on the refrigerant in this stage is equal to 0, and the net head capacity is equal to 0 too. At this stage, the enthalpy is constant throughout because the process is isenthalpic, where H3 is the enthalpy of the refrigerant before it enters the valve, and H4 is the enthalpy after it exits the valve. So H3 equals H4 at this stage. And at the final stage, the evaporation of the refrigerant, the pressure P remains constant, whereas the pressure increases. Here, the evaporator heat capacity, or QL, is going out of the refrigerated space and into the cycle. And the heat capacity is equal to the mass flow rate multiplied by the enthalpy difference, where H1 is the enthalpy of the refrigerant after leaving the evaporator, and H4 is the enthalpy of the refrigerant before it enters the evaporator. So QL equals to mass flow rate multiplied by H1 minus H4. So moving on to the flow chart.
Okay, so this is the flowchart of the Python script that we have programmed. We use 3 libraries for this coding, matplotlib, numpy, and pyromat. With pyromat, we do not need to configure enthalpy values or whatsoever in the table or anything. So it is simpler to use. So from the very beginning, the program will ask the user to input the condensation temperature, the evaporation temperature, and the mass flow rate. If both temperatures meet certain conditions, then it will proceed to finding the values of the pressure, temperature, enthalpy, and entropy at all 4 states. If they don't, it will ask the user to re-enter the correct values. Now, after the values of all 4 states have been found, it will print the values, and then it will proceed to finding the heat transfers at evaporation, condensation, the work done on the compressor, and the coefficient of performance using the formulas that have been programmed. And then it will proceed to printing the values. And then the program will then ask the user to input the theoretical heat transfer values and the work done that was found in the mathematical calculation. Now, to the decision points of percentage of error of the heat transfers and the work input and the coefficient of performance. If both conditions are met, we'll proceed to plotting the temperature and entropy diagram. If both of them are not, or only one of them are not met, then it will return to the input of beginning of the program. Next slide. I'll pass back to Mubarak.
Okay, so for the analysis and comparison, so on the left we have our theoretical approach, and on the right or in the center we have the values that we received from our numerical model on Python. So as we can see, the comparison between these 2 approaches, so the percentage difference wasn't very high. So the percentage difference of QL between the theoretical and numerical model was 0.00479%. As for QH, it was 0.025%. And for network N or WN, it was 0.088%. And the percentage difference of the coefficient of performance was 0.103%. So as we can see, the Python numerical model is fairly accurate, as the percentage difference is very negligible or close to 0. So this Python model can be used for a more professional use. So moving on. Going back to Thoheer now.
Okay, so this is the TS diagram that we have plotted from the Python coding. This is the continuation from the parts that was explained by my friend Aldeeb earlier. For the entropies, we got for the entropy at the compression, we got a 0.94566 kilojoule per kilogram Kelvin, and the entropy at the expansion is 0.391887 kilojoule per kilogram Kelvin. The temperature at the condensation is 39.37 degrees Celsius, of course, and the evaporation temperature is negative 20 degrees Celsius, as per the values that was inputted earlier. I'll pass to my friend Aldeeb to conclude.
All right, thank you, Thoheer. So as a conclusion, I'll tell you guys about the benefits of an air source refrigeration. So obviously it's more efficient because the air source systems uses the outside air as a source. It has low maintenance because of the relatively simple designs of fewer moving parts. It reduces greenhouse gases, and it also is cost effective because it's less expensive to like purchase and operate than traditional systems, making them a cost effective option for many applications. And the versatility they have, because they can be used for like variety of applications, because it's not only cooling, it can be dehumidifying, it can be like heating, and etc. Thank you guys for listening, and hope we didn't take much of your time.